Hey everybody, thanks for checking this video out here. This is the notes for day 5, where we talked about exponential functions. Oh wait, before that, we did this handout today. I'm going to post a copy of this on this forum. So if you're checking out the notes and you weren't here in class today, which that's only one person, Joaquin, and we did this handout and talked about it in class. I'll post a copy of that for you to consider. Anyway, back to the notes. We started chapter 4 today in our textbook, which is about exponential functions. We looked at this basic structure of an exponential equation and how changing one of these different little things here changes the location or shape or orientation of the graph. One of the most important things is to realize that when you have plus a k here, maybe it's not clear, this plus k, this is all one equation, times b to the x minus h plus k. This k here is a vertical shift factor of the equation, and it equates to the actual horizontal asymptote for the function. So whatever this number is, plus 2, minus 5, whatever, y equals that number is the equation of the horizontal asymptote. Also, we got into this number e. This is called the natural base. Super important number in mathematics, so just try not to resist getting comfortable with it. It's you'll be very glad you did eventually if you keep on studying maths. Anyway, so e to the x is a natural base. It's approximately this number right here. It has a lot of amazing properties. Then we talked about log functions, which are always inverses of an exponential function. In other words, the graph of an exponential function might look like this. If you took that graph and reflected it across the line y equals x, the graph of that looks like this, and that is a log function with the same base. Here's y equals 2 to the x, here's y equals log base 2 of x. So log functions and exponential functions are inverses. Let's see. Here's kind of an important thing. We have some random things here. There's more stuff about, well, you don't need to worry about that. That's for other functions. But I was just pointing out the purpose of these different parts. They work the same on exponential graphs as they do for other graphs. Anyway, here's y equals 2 to the x over here, and here's y equals 2 to the negative x. 2 to the negative x is a reflection across the y-axis of 2 to the x. But 2 to the negative x is also the same as 1/2 to the x. So 1/2 to the x and 2 to the negative x are the same exact graph. Okay? Kind of interesting. Let's see. We also talked about compound interest formula. You can check that out in your textbook, what all of those little variables stand for. This is for compounded interest, interest that is compounded at a specified rate. Here is the formula. When that rate becomes so frequent as to be nearly continuous, we use actually a different equation. So this is the equation that we use to calculate what's called continuously compounded or continuous interest. The logarithm itself, the actual structure of the logarithm, is an important thing for you to understand. First off, going back to the inverse idea, if you took y equals 2 to the x as your exponential function, switched x and y, and then tried to solve for y to find the inverse algebraically, you'd be stuck right there. There isn't really a way to solve for y in this equation. So the log expression was invented for this purpose. This is the expression, algebraic expression for the inverse of that. All right? And so here's a function, 3 to the x. Here's the inverse, log base 3 of x. Here's a function, e to the x. Here's the inverse, natural log of x. So we could say log base e of x, but we don't. We say natural log of x, and that's just the way it's written. So you kind of have to get used to these two things right here, being inverses of each other. This expression right here, log base 2 of x, means this: 2 to the y power equals x. That's kind of what we said right here. See, where was that? Trying to solve for that, okay? You're switching x and y. 2 to the y power equals x. That's what this means. 2 to the y power equals x. Okay? So that expression gives us a lot of different ways that we can use it to calculate things. Okay? And so, for example, log base 5 of 25 equals 2, because 5 to the second power equals 25. 3 to the fourth equals 81, so that means that log base 3 of 81 equals 4. 5 to the negative 1 equals 1 over 5. So log base 5 of negative 1 equals 1/5. And so on. Here's one about a radical. Log base 2 of the square root of 2 equals 1/2, because 2 to the 1/2 is equal to the square root of 2. They're just different ways of writing the same thing. Here's another one with a little bit more complicated exponent. Okay? So finally we have this snail pattern here. This is just a cute little drawing of a snail. Yes, it's a snail. Come on. It's a snail. See? There's the mouth. Snails always are smiling, of course. There's its little eye stalks sitting on, of course, a log. All right. Last thing we talked about here, very briefly, there's your assignment, and you're already looking at that, is that when you have an exponential function, we just assume for convenience and sanity that the base is not equal to 1 and it's greater than 0. Okay? You can explore this on your graphing calculator and see what happens. It's kind of interesting. The log expression also has its similar restrictions. The base should not be equal to 1, and it should be greater than 0. What that means then that this argument here is always greater than 0. You cannot take a positive number and raise it to any exponent and come up with a negative power there, or negative result. Okay? So anyway, that's it. Hope you enjoyed that. Bye-bye.